I'll introduce quickly the topic, which aims at sharing with you a few thoughts about signal processing. The original objective was to have a deadline to try to finish the work, and that didn't happen, so it's not going to be complete. But even if you don't care about satellite time transfer and positioning a satellite in space, I would like to share with you some thoughts about signal processing that I hope you can apply to any experiment. As long as you have something which is a bit of predictable, where you have a physical model, you have observations, and you want to fit parameters to your observations. So that's actually the outline. And I will apply this to a particular case of satellite positioning, because I'm always very frustrated when you read textbook. They will give you the big equations, and no one tells you how to implement them, how to use them. So you're going to see that I did put on purpose a few octave scripts, not that I expect you to read them on real time, but maybe if you're curious about what I'm showing here and you want to reproduce, you'll find the slides on my website. I'll put the URL at the end. And you can always go back into all the charts I'm drawing. You got the MATLAB script next to them to reproduce. So you might have heard that I'm curious about two-way time transfer. And so two-way time transfer is currently part of the Atomic International Time, TAI. So we have a link between Besançon and Paris, and we've been asked to try to see if we could reproduce and hopefully improve on the commercial time-tech modem from the Satra modem. And well, this is this link here between Besançon and Paris Observatory, but it's part of this whole network coordinating the National Metrology Institute over Western Europe. Currently Poland and Russia are out of the link. And all these communication this is about 3,000 kilometers, so you cannot do terrestrial communication. And so the communication is done through Telstar 11N, which is a satellite here at minus 35 degree or 35 degree west. So every even UTC hour, all these guys are talking. And the classical way is that the Satra modem, the commercial time-tech modem, it's technology from the 1990s. So you get two channels, and at any given time, there's only two people talking to each other. And if you look, there's about 15, 20 NMIs communicating like this. So basically, each one is talking for 3 minutes, and they will round robin between the various National Metrology Institutes. Now, the two topics is the reason why we're asked to work on this is that if we post-process the data, we can have all the people talking all the time. So instead of having 3-minute slots, you can have a 1-hour exchange. And the longer your measurement, the lower the standard deviation or variance. And what I'm interested in is that I don't really care that NMI share the time between them. That's their problem. But what I find exciting is that anyone with a TV satellite dish can actually get the signal. And so if you want to lock your clock to the NMI reference signals, well, actually you can do it with just a satellite TV dish. And that's actually what I would like to discuss in this presentation. So this is the satellite dish on the tripod. So this is the mobile experiment where the signal is going to a software-defined radio receiver. And to show you what the signal looks like, this is the odd UTC hour. So when there is no communication, this is the even UTC hour. So just to show you that indeed using just a software-defined radio, so something like a €100 software-defined radio receiver and your parabola dish left over, you can actually get the Satra signal that's this guy over here. And so the question is, what kind of signal processing will be needed if we want to recover time? We're going to see that there's a bit of work involved. So the outline of the presentation, so this is the mobile dish, and this is actually if you go out of the emergency exit between Christophe and Philippe's office, you will see the static dish. So this is one I used continuously. So this guy is actually continuously connected to a software-defined radio receiver and continuously monitors the two-way time transfer signals. So I just want to introduce what is the processing technique. So just to show you a little bit, and this is maybe the more generic part when people are still awake. Then I'm going to switch how to implement or how to apply this pseudo-inverse matrix calculation in the case of two-way time transfer. And this is actually what you can do with the data collected by the NMIs, which are actually publicly available from the BIPM website, or FTP site. But this is what you will find in all the publication, and it's a bit of cheating because they have this 2.4 meter dish, the same we have, and they are synchronized on atomic clocks, so basically you're in the best conditions. So I would like to see what's going to happen in the real condition where you actually use this TV satellite dish with a software-defined radio collecting data, but just clocked by its own TCXO, so very poor quality local oscillator. So what's going to be the application? We're going to see that this is all pure mathematics, and what's missing here is that there's no physics. So maybe it's good to remember that a satellite is following the rules of celestial mechanics, and can we do anything better by adding some physics? As simple as position is integral velocity, so it's not going to be too complex. But it introduces a Kalman filter, and I think we're the only lab in the world that doesn't know how to implement Kalman filter. I've been asking everyone, no one knows how to do this. So I think this is something that needs to be understood, even if you're doing optical clocks or whatever you're doing, not necessarily satellite links. A bit more physics, celestial mechanics, where we're really getting into the story, and some perspective on how this is going to occur. Okay. So to get started, let's start with high school level mathematics. You all learned in school that when you want to solve a linear algebra problem, it's as simple as, so you've got your as many equations as variable, and you can write this as a matrix equation. So you put the coefficients of your various variables on the left-hand side matrix. You've got your unknowns, and you know the solution, which are on the right-hand side. And everyone knows that the trivial solution, if all these lines are independent, so if there is no linear relationship between these lines, then you say, well, the solution is that this guy over here is the inverse of this matrix multiplied by the b term. So ax equals b, you say x equals a minus 1 b, and you get your solution. So the beauty of MATLAB is that you write this in 3 lines, and you got the solution that x equals 1, y equals 1, z equals 1. So this everyone knows. But in real life, you don't have as many measurements as you have variables. Usually you have very few parameters. Say in the satellite, you have x, y, z, the position of a satellite in space. Maybe you would add the velocity of a satellite. And you will have many, many observations. You might have hundreds of observations. So what happens if you have the case of many more measurements than 3 parameters, meaning that you have your observations are this guy over here, so you've got a huge vector B over here. You've got a few parameters, and this matrix here is not going to be square at all. It's going to be a very long, so few columns and many lines, and you would like to apply the same theory. And so what Roger Penrose and others did in the 1960s is that they created the concept of pseudo-inverse. So this pseudo-inverse is, I find it's really changed my life since I discovered the pseudo-inverse. So what the pseudo-inverse says is if you take a matrix M, which is not square, it's a rectangular matrix, and you would like to fit in a least square optimal way a set of parameters, a few parameters. So you would calculate the pseudo-inverse of this matrix M as matrix transpose times a matrix. So if your big rectangular matrix, it happens that matrix transpose multiplied by matrix becomes square. You take the inverse of this guy, and you multiply by the transpose of a matrix. And this will give you the least square optimal solution to your problem. So the beauty of this is that you fill M with whatever you want. So you're not limited to just AX equals B, because A is, we saw earlier, just your linear coefficients between the various x. But in this particular case, okay, you can do it. So let's take the case of a linear relationship. So we say we have our observations here, and we say that the solution, so this is the solution that you expect to get, is something like AX plus B. So you take a noisy, so you add some noise to your actually Z measurement, and you say, I would like to find the optimal solution to this linear fit. And so exactly like we just said, so either you write it by yourself, M transpose M minus 1 times M transpose, or under Octave and MATLAB, you've got P in, and if you look at the source code, P in is just what we just said here. And so pseudo-inverse of your matrix times the measurements, so Zm is the noisy measurement here, well, you actually get the matrix you see is, well, we want to find something which is AX plus B, so a linear relation. So you say, well, in this particular case, my first term will be the constant, so it's just ones, and the second term will be x, so 1, 2, 3, 4, because it's the linear evolution. You want to have ax plus b, so your first one is going to be the estimate of b, and a, because a times x will multiply to try to fit at best your Zm. So you take the pseudo-inverse of the matrix here, multiply by the observation, that gives you the solution. And the solutions are your two coefficients, A and B, in AX plus B. So you see in this case, for example, I just took random value, A equals pi, B equals 42, and the solution, the red line here is your noisy signal, and the yellow line is your estimate. So you get something which is estimated as 42.14 instead of 42, you get 3.15 instead of pi. So the solution is not too bad. So here you got your parameters, and then you might want to know what is the quality of your fit. So how does your estimated data compare with the measured data? And to do this, you take the matrix of your, so this is what you want to fit. So you have your constant term here and your linearly evolving term here, and you multiply by the coefficients, so the parameters that you just find. And mat times so will be a vector which has the same length as Zm over here, and you can plot it. And hopefully this gives you the same solution as, so this is your true solution in yellow, so this is the thing that you have here, and the blue curve is your estimate. So you see, in the trivial case of the linear fit, it works. Why do I say it's beautiful? Because no one said that you had to just put in the matrix term here something that is linear. You can put any physical insight if you know what is the relation between your quantities. The only thing is that these quantities must be linearly dependent to each other. But if you want to fit a parabola, well, the first term of your matrix will be the constant term, the linear term, and you've got the quadratic term. So this is the one that scales as 1, 4, 9, and so on. And again, same story. I took a vector. I created my solution, my real solution, what I want to get, the x squared. I take a noisy signal. My measurement is the real signal plus some random noise. And again, same story. I take the pseudo-inverse of the matrix multiplied by the observation. And if I plot the real solution, so the measurement with respect to what I actually estimated, again, you see that the yellow line is what you should get, and the blue line, the blue line is the measurement, the red line is the estimate, and the true solution is the yellow one. So again, it works. And final solution, just to show how generic you can do this, is you say that you have a loading capacitor. So you know that, for example, you've got a voltage offset and a scale of your loading capacitor. Same story, I'm not going to follow it again, but you get your exponential. So just be aware, here we're taking the linear dependence. Of course, you will not, using this technique, be able to adapt tau, the time constant, because this is inside the nonlinear term, so that's not going to work. So you see, the generic way of doing this is you create your matrix with whatever you want, and actually, when I'm doing radar, you want to detect the transmitted pattern. This M here can be time delayed. The first time I discovered pseudo-inverse was when you wanted to the direct signal interference cancellation. So you know that you're sending data or you're sending a signal towards target, but you want to cancel the direct communication between the emitter and the receiver. And to do this, well, you would actually fill the M matrix with time-delayed copies of a transmitted pattern. And by doing this, you find the weight of the transmitted signal and the received signal, and you can cancel it, and you only recover the far-field targets that have reflected the energy. So this M construction here is the core aspect. And once you understand how to construct M, you take the pseudo-inverse of M, you find the weights, and you multiply the matrix of the base that you want to find with the solution to check how it fits. So you see that this can be adapted to basically any kind of problem. And actually, you don't need to do this only in 1D. You can actually do this in 2D. You generalize. So I'm not going to go into detail, but same story again. So you've got the true function, which is something like, you see, this is my measurement, x plus y squared. So you create a 2D function. And it's exactly the same thing. You say, OK, each one of these sample is supposed to be at x plus y squared. So you create, again, your matrix, which is, well, what should it be? It should be a constant term. It should be a linear term. It should be a quadratic term. So you see here, you have a linear term. You have a quadratic term. And the same story again. You say, I take the pseudo-inverse of this matrix, and I take the solution of my observation multiplied by this matrix that I've inversed. And same story again. You find the parameters, and if you multiply the parameters by this matrix, including the basis on which you're projecting your data, you find the estimate of the fitted data. So you can actually do this in multidimensional problems in the same way that we did it in the single dimension. Now, very often when I'm doing this, I wonder what kind of error bar should I put on my fitted parameters. Okay, you say I measure the voltage, but you fitted something and you say, what is the accuracy with which the fit converged? So you can actually do the story here is that you will calculate from your observation, you've got the estimated data, so you take the sum squared error, which is what is the difference between what I estimated and what I actually measured. And you take the mean value, so you divide by the number of degrees of freedom. So there I just took what you find on the Wikipedia webpage, which is number of degrees of freedom is number of measurements minus number of parameters. So if you do a linear fit, AX plus B, you have two parameters, you have n measurements, so your nu here would be n minus 2. So basically for large measurements, this will be very close to the number of degrees of freedom. But you also see that if you're making a line go through 2 points, the uncertainty is infinite because nu will be equal to 0. You have no idea how accurate your line is because you only had two points to go through. And so the uncertainty on your parameters will be diagonal of the M matrix that we just saw earlier, so M transpose M minus 1, and instead of multiplying by M transpose, this time you multiply by this mean square error, and that gives you the confidence interval. It's proportional factor because here you've got, whether you want 60% uncertainty, 90% uncertainty, you will just scale this guy over here. But okay, if I remember well, if you put 1 over here, it's the student distribution, inverse student distribution. 1 will be 80% uncertainty. So you can do actually the calculation. If I take again the same story of my loading capacitor here, the solution is supposed to be 1 and minus 1 because I took something like 1 minus exponents of minus x. I added some noise, and you see that at the end, it gives me a solution which is 0.99 plus or minus 0.013. So indeed, 1 is inside the interval, and 1.02 plus or minus 0.06. So again, the beauty here is that you can actually give a confidence on your parameter estimate. Okay. So if you're not interested in satellites, that's everything I wanted to tell you about signal processing, and I believe this can be applicable to any kind of measurement where you have parameters, you have observations, and you would like to fit the parameters to your observation. Now, how do I actually use this? Because all this is nice on free-liners of MATLAB, but how do you actually work on this? Now, let's take the case of two-way satellite time transfer. So we've got this guy over here transmitting to the satellite and beaming back to the second receiver. And in two-way time transfer, the idea is that the two people are doing this at the same time. So, and actually same is very important in this story. So the two people are working simultaneously to send the data towards the satellite and go downlink. And because when you're doing two-way time transfer, you will take this plus this minus this plus this. Actually, if you do it at the same time, the motion of the satellite looks like frozen space. Your satellite is in geostationary orbit, but geostationary, we've already seen, means that the satellite is moving around its equilibrium point at something like a few nanoseconds per second, and say you have 1 nanosecond offset, 1 second offset between this guy transmitting and the other guy transmitting. Well, the satellite will have moved by 5 nanoseconds, or 1.5 meter if you prefer. And so either you're very accurate in the way these two guys are synchronized, this is what we're doing in our two-way time transfer system, or you try to estimate the velocity and the motion of a satellite. And that's actually what I'm doing, because the next item here will be, I want to do passive measurement, and if I'm doing passive measurement, I'm not actively probing the satellite, and I will need a way to subtract the satellite position. Remember, the satellite is moving by something like 30 kilometers around its equilibrium point. And electromagnetic wave propagate at 300 meters per microsecond. So 30 kilometers is 100 microseconds. So if you're not careful, your satellite is introducing plus or minus 100 microseconds in your time transfer. And we want sub-nanoseconds. So of course, there's no way we're going to reach let's say sub-microsecond, at least if we don't cancel for satellite position. So that's the whole story about finding the satellite position. You want to cancel the fact that this satellite is moving around. These guys are fixed on the surface of the Earth, and by moving around, well, you introduce some delay, and if you want to do time transfer, you need to remove this delay, and the only way I'm familiar with is to estimate the position of a satellite. So the question is, how can I find the position of a satellite, and expressing the position of a satellite over the surface of the Earth is not a very convenient way of doing things. So if you look in the literature, what people will do is they will write the problem in Earth-centered coordinate system. So that's your ECF, where you say this guy here is with respect to the center of the Earth. These two guys at the surface of the Earth are at coordinates of the surface of the Earth. And very obviously, the distance between a ground station and the satellite is the difference of the abscissa, the difference of the ordinate, the difference of the altitude squared and square root. And so the only thing you're saying is when you're doing two-way time transfer, you have rho I plus rho j seen by one satellite, rho j by one station, rho j plus rho I seen by the other guy. You take the difference, and if all goes well, you're only left with the clock difference between the two ends. But this is not linear at all. So how am I going to apply what you're saying here in what I just said earlier of linear algebra solution? And so, as usual, you need to take a Taylor series and to linearize your problem. And so remember, your Taylor series is that your solution, so we're familiar all with Taylor series in one dimension, but you can do it in any dimension you want, just remembering that your function at xyz is your function at the position you're interested in, plus a minor correction at this same position, dx, and for all the other dimension. And I remind you, I had to ask Wolfram Alpha to do this for me. I did not remember, but Taylor series of a plus x squared. So a plus x squared is this guy over here, okay? xi squared will be my constant term, and I will get here the quantity that I want to analyze, the position of a satellite in space. So you know that your satellite is more or less around its equilibrium point, and you want to know how much it's moved around the equilibrium point. And so you end up having a Taylor series development where you have a constant term here, which are these guys, and you get something here multiplied by x, which is this guy coming out. And because in our case, a squared plus b will be the sum of xi squared, yi squared, zi squared, is going to be actually rho, the theoretical distance if the satellite was located at its equilibrium point. So I did this, and I was super pleased to find a way of linearizing the problem. And I was super pleased until I realized that in all ESA books, you will find this everywhere. Everyone who's doing GNSS is expressing the problem of GPS localization by saying, I have a distance, and this is the distance of a satellite, of a GPS satellite over the surface of the Earth, and you linearize this. And actually, if you're interested in the problem of using your mobile phone for actually solving the GNSS equation, there is a very nice white paper by European Space Agency on how to use your road measurement from your mobile phone to solve the GPS solution. So basically, everyone knows this, but okay, it's always nice to rediscover things that people knew. So how do we apply this knowledge? So this is why I'm saying this is all GPS upside down, because in GPS, you've got all the satellites which are synchronous, and you want to know where you're located on the ground of or actually all the satellites are broadcasting the time difference from the satellite, and you want to know where you're located. Here it's upside down because we know where the NMIs are located, and we want to know where the unique satellite is. But the problem is very similar to GPS. So this is what it ends up being. You say that you've got the speed of light times the two-way time transfer. So you have the time from the first observation plus the time of the other observation. You express this as the range, so the range to the ideal position of a satellite in space. And we take our Taylor series where we have the theoretical position, we have the ground station location, and we have dx, dy, dz. How much has the satellite shifted with respect to its ideal position? This would be the equilibrium position of a satellite, and this is the shifting position of a satellite in space. And okay, so now we have our expression because these are all measurements. We know where we are, we know where the satellite is supposed to be. This is station I, this is station J. And all we want to solve is dx, dy, dz, the offset of a satellite with respect to its equilibrium location. So if I take all this thing here and I put it in terms of matrix equation, you end up having something that is dependent on dx, x0 minus xi divided by rho I. Same thing for j, which is this guy over here. We do it for the second order terms. But now there's another problem. So this is super easy because this creates a diagonal. Okay, we have multiple measurements, and this will mostly be along the diagonal. So basically, you have three diagonals that will be filled, which is x, y, z, the position of a satellite for each observation. Now there's a little trick here, is that the people who are broadcasting, they put cables between their reference signal and their parabola dish. And they introduce delays, and you don't know what this delay, or at least you would not want to know what these delays are. Actually, if you look at the BIPM website, these delays are published, but let's say it's an open problem to find the delay of a transmitter, of a receiver, and the satellite is called a bent pipe satellite, so it gets 14 gigahertz, it downlinks 11 gigahertz, and you don't know how long it takes for the signal to go from the uplink transponder to the downlink transponder. So we have another term here, which is the delay introduced by a satellite. And this is kind of annoying because this term here appears in every observation. You will have in every observation these time delays, but for different I and j. So you're creating this additional term here, which is what is the time delay introduced by observatory I when it's talking to observatory j. And these guys here will be a big column filled in all the observations. So to try to put something concrete in all this discussion, this is actually what your matrix looks like. So you see we want to know these quantities, which are the time delay of a transmitter on observatory number 1, the receiver number 1, transmitter number 2, receiver number 2, all the observatories. So these are all the things that you will find for all observations. And then you will have something which is what is the position of a satellite for observation number 1, position of a satellite for observation number 2, and this will be just along the diagonal. So these columns here, which are 2 times the number of observatories, uplink and downlink delay, these will be always filled in all observations. And then you've got just these 3 diagonals here, which are the 3 observations that you're making each time you want to estimate the position of a satellite in space. So, and at the end, your observation is your two-way time transfer. So you're observing the time from satellite I to j, the time from satellite j to I, minus the theoretical range. So what these things here should cancel out if the satellite was nice enough to be resting at its parking position. And of course, it never happens. So here you have a x equals b, and this is the x you would like to find where you've got these quantities you would like to identify. So we do, as we just said, x equals p inverse of a times b. So p inverse of these guys over here multiplied by b, the observation, should give you these quantities. This would be more or less simple, except we just said earlier that the stupid SAT can only do measurements 2 by 2. So actually, you would like to have all these observations at the same time, but in practice, there's only 2 people who can talk at any given time. So you actually see, if you download the BIPM document, you go on the BIPM FTP site, you can get the SAT measurement. These are published. There are open data that you can access. And here you've got the time. It's a modified Julian date, minus 30,000. I'll show you later why 30,000. You've got the transmitter index, the receiver index. So these are the various satellites, various observatories broadcasting. So this is the emitter, this is the receiver. And you've got the two-way time transfer measurement. And what you actually see is that at any given time, there's only 2 guys talking to each other. And then you run another set of measurements. And they're not synchronous because only 2 people could talk at any time. So the annoying thing here is that if you want to solve your problem, you assume that the satellite is moving linearly and you're going to interpolate. So you actually must interpolate what the other observatories would have observed if you want to have enough observations to solve the 3 quantities x, y, z, because if you only have 2 observatories and 3 x, y, z, you don't have enough parameters to solve. So you do this, and this is actually what you end up getting. So these are the raw positions that you download from the BIPM website. And in this experiment, what I did is, let's take all the European observatories and let's remove the guys from Switzerland, because in Besançon, we're close to Switzerland. So let's get the guys from Zurich out. And let's see what we can estimate as the satellite position in space. And then let us subtract the contribution of a satellite position in space to the observation of Switzerland. And because, on the other hand, we do have a real observation from Switzerland, we can subtract the 2 and see what is the leftover delay. So you see this is the satellite motion in space. And so the blue ones are PTB, Observatory of Paris, the Spanish guys, the Swedish guys, all communicating. And the red one is the Swiss guy. So basically what you're seeing here is the satellite motion around its equilibrium. You see here, it's 24-hour period, of course, because the satellite is moving because of a sun and moon motion. And this is the subtraction once you've removed. And, well, I tried to do various. I told you that there is a fit. You need to estimate where would the satellite be, or what would be the delay introduced by the satellite motion in the other observatories which are not talking. So I did a few variables, so first order linear fit, second order linear fit, this kind of stuff. And this is the residue that you're left with. And so what you see is that if you were not to remove a satellite contribution, you would have something like plus or minus 30 microseconds. And after you remove the satellite motion, this is just mathematics, no physics in all this. You end up with something like plus or minus 50 nanoseconds. So you see we go from 50 microseconds to 50 nanoseconds by estimating the satellite position. So we gain 1,000-fold, which is not too bad, I think. So this is the residual here of the time between observed Swiss time minus the estimated Swiss time. Now, I should tell you, this is far from state of the art. Carsten Rieck has published that he can get 1 nanosecond at the end, but you see that with very basic mathematics, you can get 1,000-fold improvement. So this is all a lie, because I'm using the BIPM data, and this is actually what people are publishing. They take the BIPM data, they do all their fancy signal processing, and they say, look, I find a nanosecond. Yeah, but in real life, you're not going to have a 2.4-meter dish. You will not have an atomic clock. You will have a shitty TCXO running an SDR on a 60-centimeter dish. Well, what do we get in real life? So actually, when you're doing passive two-way time transfer measurement, the problem is slightly different because you've got these two guys broadcasting towards the satellite, and the satellite is illuminating all of Europe. So as long as you're inside the illuminated area of the satellite, you're going to get something. So here we're in Besançon. This is, say, Paris Observatory, or ideally this is Spain, ROA. These are the Swedish guy, because this is where you have the biggest opening, and we're here in Besançon. So we're looking at the Spanish guys broadcasting to the satellite and beaming down here, and we've got the guys in Sweden beaming up and looking down over here. Now, we are looking at the difference between Spain broadcasting over satellite minus Sweden broadcasting towards satellite, and the problem is slightly different. You remember, when we do two-way time transfer, we have a sum, because we're broadcasting here and we're receiving the sum of the two contributions. But now, if I'm looking at Spain with respect to Sweden, I'm going to subtract the contribution. So now, before we had Ti plus Tref, now we have Ti minus Tref, because this guy here has one contribution that you cannot eliminate. It's the common path between the downlink, between the two downlinks. So it just expresses a little bit differently the equations, but you see that again, we can linearize, have dx, dy, dz, the same as before, but I put here with arrows the signs that have changed with respect to the previous challenge. And actually, because you're doing the subtraction, if there is a delay introduced by the satellite, well, this time it's going to be cancelled out. So we have one parameter to remove because the satellite common delay will be subtracted between the two guys. And actually, this means that this guy here is unable to observe this time delay unless you're doing a calibration. So like we were doing with TimeTech, you need to have a mobile station calibrating this time offset. So you only end up having, with this difference, you only get the transmitter 1 contribution and transmitter 2 delay contribution, but there is no receiver contribution and there is no satellite delay contribution. So same story as before, you put this as a matrix and you solve this. And SATRA was definitely not designed for passive time transfer, because the pulse repetition interval in radar, we call this pulse repetition interval, is the longest path, unambiguous path to a target. And the faster you send pulses, the more ambiguity you have. And in the case of the SATRA modem, TimeTech decided to have 4 millisecond long pulses or code length, and the signal takes 260 milliseconds to go from ground to satellite and back to ground. And what you see is that actually 260 divided by 4 milliseconds, we have something like 60 pulses in the air. So you're ambiguous by a factor of 60. You don't know which one of the pulses has gone up, but you do know more or less where the satellite is located. So actually your ambiguity is not 60 pulses, but it's actually plus or minus 1. So you need actually to remove plus or minus 1 code length, because the code is too short and you cannot have an absolute estimate. So in our implementation of two-way time transfer, I extended the code duration to 40 milliseconds so that we have a less ambiguous measurement. And so actually what you end up getting, and actually I find it even fascinating that it does converge. So this is my observations. This is actually the observation I'm doing with my satellite dish. And when I'm applying the same processing technique as I just showed you earlier, well, it more or less works. So you have a plus or minus 30 microsecond, which is a satellite motion in space. But with the smaller dish that I have, and especially with a poor quality local oscillator, well, I can only reach plus or minus 5 microseconds. I cannot get the sub-microsecond result I was looking for. So math will not be enough to find a solution. We need to find something a bit better than just math. So that's your leftover. So this is actually 20 microseconds, but if you take the standard deviation, it's going to be a bit less. So basically plus or minus 5 microseconds standard deviation on your time transfer. Okay, so at the moment, we only did mathematics, and we never discussed physics. So what can we do? First of all, if you read how people solve GPS, they actually iterate, because you're doing a Taylor series, and your Taylor series is only as good as the linearization you did. And usually in GPS, they will iterate this 3 times. So they will make 3 times the iteration until they converge. But in our case, the problem is that in GPS, time is a constraint. You know what is the time delay. You only need to solve the position. In our case, we have the time delays and the position. And so we're not allowed to iterate, because actually you see that the position changes, but then the time changes, then the position changes, and it just keeps on changing both at the same time. So that's not going to work. So what else can we do? The first thing you might think is, okay, maybe what we can do better is, if we know the position at every time step, well, here we're measuring the position one after the other independently of each other. But we're doing measurements and known time intervals. So if we were to know the speed of a satellite, we would say position is the integral of speed, and we could help the solver try to identify the position of a satellite. So this is actually the velocity of a satellite measured by the speed at which the code is shifting. Remember, we're working with a transponder, which is a band-pipe satellite, meaning that the satellite is introducing a frequency offset between the uplink and the downlink. And it happens, I don't know why, that this frequency offset is dependent on the season, is dependent on the illumination of a solar panel, is dependent on the satellite temperature. So you cannot use the carrier frequency. You need to use the code. But the code, because the satellite is moving, is slowly shifting. And if you look at how quickly the code is shifting, you actually get the speed of the satellite, which is a few nanoseconds. You see this is, well, it's actually moving on the 3rd decimal, so it's moving by a few nanoseconds per second. But you see that this is my software-defined radio receiver. And first of all, you see that there's a bias, 2 ppm. So the clock offset is 2 ppm. And secondly, you see that it's shifting randomly. Well, this is a temperature-controlled crystal oscillator, so you just have your poor quality crystal oscillator, which is drifting over time. This is all known. So, okay, let's say we're in the time and frequency department, and we have hydrogen maser, so we get rid of a TCXO, we clock the software-defined radio by a hydrogen maser. Now, to me, it's always funny why we're doing all this. And I like to show this. I'm sure it's obvious for everyone, but this is your TCXO drift. So first of all, you have 2 ppm offset, and this is the scale, so 20 ppb. And if I shift from my TCXO to my hydrogen maser, you take the same scale over here, so this is your 20 ppb, and you see that you have 0 offset by definition. So if you only wonder why people are buying high stability oscillators, if you want to track a deep space probe, well, this is what you get with your shitty crystal oscillator. This is what you get with your high quality reference clock. And actually from this, you hope you can do some Doppler shift. And from the Doppler shift, if you know that your oscillator is not drifting, then you attribute the drift to the target. So can I estimate the velocity, because I've got all these guys beaming a signal to the satellite, and they're distributed over Europe. And can I estimate the velocity vector, not just the velocity magnitude, but the vector of the velocity, because this is what I need to predict the position. And if you look at the classical bistatic radar Doppler shift, so this in a bistatic radar, you've got a transmitter receiver, which are not located in the same space, in the same location on the ground. You've got a target, and what is known from bistatic radar is that the Doppler shift is given by the angle beta between transmitter, target, receiver with respect to the motion of a target with respect to this beta. And this is what you will find in all textbook on bistatic radar, where the Doppler shift is the uplink frequency plus the downlink frequency, velocity of a target divided by the speed of light, cosine of delta, cosine of beta over 2. Now, you do the calculation in the case of Europe, and you remember that Europe is about 3,000 kilometers wide, But the satellite is 36,000 kilometers up, and because actually it's over the Atlantic, it's 35,000 kilometers. So you do the calculation, and you see that this beta angle here is close to 0. So basically, the problem is very poorly conditioned because you're basically doing a monostatic radar measurement, and a monostatic radar measurement cannot give you a vector, it will only give you a magnitude of the velocity. So the problem is very poorly constrained, and if we look at this in terms of what would be the requirement if you wanted to get the velocity, well, I remove the monostatic measurement because, okay, the satellite is moving, it's created Doppler shift, and this is just a magnitude, we're not interested, we want to get a vector velocity. And what you see here is that you would need something, so this is nanosecond per second, so you would need 0.2 picosecond per second resolution. And at the moment, this is below what I can measure. So it's hopeless. I'm not going to get the velocity of a satellite by just measuring the offset. So this brings me to the last part of my slides, where in Kalman filters, in GPS receivers, everyone is using Kalman filters. So my initial insight was, let's make a Kalman filter for this problem. Disclaimer, I'm not going to succeed. I don't know how to do a Kalman filter. So I went for a basic example just to learn how to do it, and I asked Gonzalo to help me, just to figure out if you have a falling ball. How do you solve a falling ball problem using Kalman? And this actually is the right way of doing things, because here you introduce the physics. You know that the satellite is moving along the celestial mechanic physics, so you put a real physical equation. You put some evolution, so this is the evolution of the position. You get the evolution of velocity, and you get the evolution of the acceleration. So some of these variables might be hidden. In this case, for example, acceleration is unknown, or is not something I want to change. In the case of a satellite, I might not know where the moon and the sun are located. So I will just say, let the acceleration be tuned by the Kalman filter. At first, I might say the only observation I have is the position. So position is visible, velocity is not visible, because I just showed you that the Doppler, I cannot find it, and acceleration is not visible. So you've got hidden variables, velocity, acceleration, and you've got visible observables, which are, in this case, the position. Now, you need to give Kalman filters two quantities. One is super easy, is your measurement noise. So you plug in your voltmeter, you look how much the voltage is changing, and this is the standard deviation of your measurement. So that's easy enough. But the point of Kalman filtering is to say, let's compare how a model evolved with respect to noisy measurement. And Kalman tries to optimize again to weight the contribution of the model with respect to the observation. So what Kalman will do is say, okay, my model is very poor, my observation is much better, so let's forget about the model. But if the model is converging better and the noisy measurement is degrading the observation, Kalman will say, I will rely more on the model than on the observation. And so Kalman filtering asks you to give a model noise. And Gonzalo confirmed, because every website is giving a different formula for the process noise. And Gonzalo confirmed this is where you put the black magic. You estimate how poor your model is, or how much you allow Kalman filter to leave the model when it says the observation is better than the model. So once you've established the rules that go from step n to step n+1, so the physical evolution of your system, once you've decided which quantity is observable and which quantity is not, you're allowed to have hidden variables. Once you've decided what is the model noise and the observation noise, then it's all rules that you just follow. And actually, if you're using MATLAB or Octave, you have Kalman filter, and it just runs it for you. I wanted to learn how to do it myself, and Gonzalo was laughing, asking, why don't you use the Kalman toolbox? And because I wanted to learn, but it's all implemented in the automation toolbox. So basically, what they tell you is you have a noisy observation. This is something that you have a real position to which you add some noise, and that's your sigma z over here. Then you say you want to predict the new positions. You apply the A matrix going from estimated position previous to the new one. Then you estimate what is the noise. So the covariance is the various noise between all your observations. You update your state, and you calculate a gain. And actually, the gain is where you have a tricky part, because you have, again, this inverse. And we just saw that inverse is always annoying to calculate. But if you just look at what it means you're taking the ratio of the model noise divided by the model noise plus the observation noise. So what Kalman is doing is it's tuning the gain to say which one is more reliable. Is it the observation or is it the model? And finally, you update your prediction and you update your covariance. So actually, the noise estimate of Kalman will be constantly updated. And you just keep on running this. So here, for example, this is the real solution is the dropping ball. We all know half of GT squared is your ball that is dropping. Now, what we do here is we say, okay, we want to have the velocity. The velocity, remember, is a hidden variable. The only thing we know is we might want to have the acceleration. And in this example, we say acceleration, the new acceleration is equal to the old acceleration. So G, the gravity constant, is not changing. You know exactly what is the gravity constant, and you don't allow it to change. And you get something which is your position error, your velocity error, and your acceleration error, which is close to 0 because you say acceleration is known to be equal to G. And you've got the residual. So you actually know what is the residue. You know how much noise you're left with. OK. So now let's say I would like, first of all, to say, OK, I don't want to only have a position. I also want to observe velocity. Let's say I can observe the Doppler shift. And the other thing is, I might say, maybe the acceleration is not something that is known, but I might have some noise on the acceleration. And this is the case of a satellite, because I don't know how a satellite behaves, but I might say the acceleration of a satellite is something I let Kalman estimate. So I will not, again, I told you I put the code because if you want to repeat it yourself, but you see that this whole calculation here fits in this number of lines. So you take the standard deviation on your acceleration, on your position, you know what is the acceleration is, you put all the vectors that we just said earlier, so your initial state, you're at position 0, velocity 0, acceleration g. You know that the only thing that you can observe is the position. You've got the matrix that gives you from xn to xn plus 1, so the position plus the integrated velocity plus the double integrated acceleration, the evolution of the velocity, the evolution of the acceleration, and you just run Kalman, as we just said, together, and it will give you these charts. What do you change in this line of codes if you're going to say, now I have a Doppler shift, now I want to observe the velocity? It's as simple as just adding, okay, now we've got a new term, which is the velocity, gt. We got a standard deviation of the velocity that we introduce in R. You remember that R is this guy over here, so R is this measurement noise. So now R has become a vector. We've got the uncertainty on the position and the uncertainty on the velocity, and that's it. Everything else remains exactly the same. You've added the fact that you can observe position, you can observe velocity. Be careful, because at first I put the two guys together. If you put 1, 1, 0, it means you're measuring a combination of position and velocity. That's not the case. You're measuring position and velocity, so it's a 3x2 matrix. And you just run the same story. And if you look before, we had plus or minus 60 meters, we had plus or minus 30 meter per second. Now if I estimate the velocity, well, I observe the velocity, so of course I have much less uncertainty, and less uncertainty on the velocity means less uncertainty on the position. And so finally, to conclude, you can let the acceleration be a free degree of freedom, but if you let the acceleration free to tune by Kalman, of course you're going to degrade the result, because you say you lost information. You knew before that the acceleration was the gravity constant, but now you let the gravity constant change a little bit, so you're going to degrade your position and velocity quality, but at least you let your model try to find the right solution if there was some error between the model and the estimate. Okay? So you can go through the examples, and you'll see I just highlighted with arrows where the changes were from one example to the other, so you see how you can add various parameters. And so finally, to conclude this whole discussion, I wanted to avoid celestial mechanics because it's too complex for me. We're not a celestial mechanics lab, and we don't know how to do it. There are two open source toolkits, GMAT from NASA and OREKit from the European OREKit. So these are open source celestial mechanics, and I've been struggling for the last couple of months to try to learn how to use them. But if you don't work at NASA, or if you're not working at CNES, you just cannot understand this by yourself. You don't have a culture and you don't have a knowledge. These are just impossible to understand. But if we look at Carsten Rieck work, they say that the robust detection and mitigation of satellite orbit maneuvers are the most important, and they have the prediction have a lifetime of published orbit, which is only valid for something like 4 hours, which is 1/6 of a window. So one of the errors I was doing was to try to take this big observation over 1 week and to inverse the big matrix of 1 week observation. And actually what Carsten Rieck says is you should be working 6 hours by 6 hours because there your model will be still valid, and after a very long duration you have perturbation that accumulate and it's not going to work. And there's another work of these Chinese guys who are using geostationary orbit determination using Sartre, where they basically say the same story. They say that because of solar radiation pressure, because of various unwanted effects, your validity of a model will be only correct for about 6 hours. So at the end of the day, if you look at the literature, there's no way out. You need to introduce the orbital parameters and predict a real orbit and not just a falling ball as I've been doing. And I contacted CNES, and yeah, they told me you have to make an orbital model and tune the parameters using the tools we just said, but I don't know how to do it. So yeah, that help is sought to solve this. So to conclude this discussion, I wanted to try to show you how you can maybe use some of the mathematical techniques I've been learning in my satellite location solution by using pseudo-inverse for identifying linear combination of any function. I tried to apply this technique to two-way time transfer, and I saw that actually you need to introduce some physics. And then we end up having what everyone knows. You need to use a Kalman filter. And as I was so Kalman was invented for Apollo, so to get the astronauts on the moon. But if you look, actually, it's beautiful because there's a history of Kalman filtering in aerospace. And they tell you that GPS is actually, from the perspective of a DoD, is just one big Kalman filter. So you're using Kalman on the ground on your receiver because you say, I'll observe a satellite and I want to know my location in space. But the DoD, they want to know what are the constellation status. And so from their perspective, the GPS is described as one enormous Kalman filter, which has a large system state vector, including the trajectories of a 24+ satellites. So we really need to learn how to use these tools. Everyone's using them except us, so that's something we need to know. And finally, just if I can get your attention, NIST has published at the end of last year, beginning of this year, NIST will be leasing their two-way time transfer facility. So actually you can rent for €6,000 a month, plus installation of a parabola dish. NIST will give you traceable two-way time transfer synchronized data. So you've got the NIST time, you've got your time, you've got NIST time, and you can have NIST traceable time by implementing two-way time transfer on your roof. And my question is, okay, let's say they're successful in their attempt. They rent on Telstar a given bandwidth, but especially a given power. We're not allowed to broadcast any power. We know how much power we're allowed to broadcast. And these guys, if they have like 100 people subscribing to a service, how do they limit the amount of power that's going to reach the satellite? But that's an open question. I don't have the answer. So that concludes what I wanted to tell you, and I thank you for your attention if there is any question.